So today we're going to cover two of the next two of the top 10 vulnerabilities in smart contracts. The first one we're going to cover is arithmetic issues. So these can be classified as integer overflow and integer underflow, and unsigned and signed integer confusion. And it can turn a lot of benign-looking code paths into vectors for theft and denial of service. So far, the amount that has been lost to this kind of issue in a smart contract is about 150,000 ETH, or $30 million of cryptocurrency at this time. Here's an example of what might go wrong. You have a contract, it has a withdraw function, and it allows you to retrieve ether that you have given to the contract prior to the withdraw, just as long as the balance that remains in your account is positive after the operation. So, reasonable thing to ask for. An attacker attempts to withdraw more than his or her current balance, and the check and withdraw is done with an unsigned integer. And this results in a condition that's always positive. So the attacker can then withdraw more than allowed, and then the resulting balance will underflow because the check is bypassed. And then because it underflows, you end up with a balance that's orders of magnitude larger than it should be. So this has happened last year. This is a batch overflow bug. We're going to look at this particular vulnerability in the next slide, but basically this is an ERC20 smart contract, and depositing to the smart contract was suspended, as well as withdraws because of this. The attackers were able to generate an extremely large amount of tokens and then deposit them into a normal address. So here's an example in code. You have a withdraw function. It looks at the amount, and it requires that the balance of the sender minus the amount is greater than or equal to 0, and if so, you can do the transfer. So message sender transfer, that amount, and then balances, and then you deduct that amount from the balance. So what is wrong with this code? It looks pretty good, right? Can anyone... Yeah, you're using a uint. When is this ever going to be false if this is a uint and that's a uint? If you remember 201, again, you might have just tried to shut off what 201 was about, but yeah, if you have uints, uints are never negative. So if you do something like this, this thing is always true. Looks good, but is always true. It looks like you're doing something. I'm validating. I'm doing some assertion up front, but you're really not. So yeah, the uint makes this require statement pretty useless. So if the attacker has 5 tokens, withdraws 6, ends up with 2 to the 200. So assuming this is a 256-bit integer, then it ends up with 2 to the 255th minus 1 tokens in the balance, and then you can wipe the contract out. What would make this code problematic? Take a look at that. So popping an array of things, I want to get rid of the, say I have a mapping, and I push and pop into that mapping. And as long as I have something in this array, I will allow you to pop, decrease the array by 1. Yes? The what? Yeah, it works if it's equal to 0, and then this thing will go negative. And so the impact of this is all of a sudden, if you have basically an array that's 2 to the 255th long, and some part of the code is actually going through every element of that array, you basically can brick a contract by setting its array to that huge number. Then there will be not enough gas in the universe to be able to execute a contract that, like, for every element in that array to do something. So, okay, That's actually 2 code vulnerabilities, not 1, but oh well. Here's another one, and this is similar to the slide 2 slides ago for that ERC20 bug. So here's an overflow code example. This code seeks to send to each address in receivers. So I'm a sender. I want to send several addresses the same amount of money. Say I'm trying to distribute profits equally amongst my partners. So I send an array of receivers, and I say I want to give each one of these receivers 1 ether, some value amount of ether from this contract. I calculate in line 257, so count is the length of the receiver array, and then in 257, I calculate the amount that I'm trying to transfer as the amount in the count times the amount of value that I'm going to send to each one. I also have these 2 require statements to make sure that I can only transfer to up to 20 receivers. So it's greater than 0 and less than 20. And then line 259 is ensuring that the amount that I'm going to transfer to each receiver is greater than 0. Moreover, that I have enough money in my balance, which is here, I have enough money to send this amount, right? I want it to calculate the total amount I'm going to send, so this has to be greater than that amount. And then if so, if these 2 things pass, then I'm good to go, right? So I can basically subtract the amount from my balance, which is here, and then for every receiver, so from I is 0 to I less than count, which is the number of receivers, I'm going to transfer to each one of these receivers, each one of these, a value amount of tokens. So then we'll update our balance here. So line 263 updates the balances. So I update mine, and then I update the receivers to add value to their account. So are there any errors here? And if so, what are they? Yeah.
You're not calculating the stuff you need for the gas to run the contract?
So I am, yeah, that's correct. I'm not calculating gas. So I implicitly limit this to be less than 20 so that this for loop will have enough gas. So I've already figured out that the amount of gas needed to calculate this thing 20 times is within the limit. Yes?
If value is a large number and overflows when you multiply it by the count, then the amount calculated could be small, but the value is really high.
Yeah, that's exactly it. So if value is super high, close to the maximum size of that integer, and then count is like maybe a small integer. If you multiply the count by this large value, your amount is going to overflow and give you a tiny integer. Okay, so yeah, that's the contract exploit. You can pass 2 receivers into this batch transfer. Say I want to pay 2 receivers, but I want to pay each one 2 to the 255 in value. That's 1 with 255 zeros at the end of it, right, for your 256-bit integer. And if I do this, what is the value of amount? I set the number of receivers to 2. I set the amount I'm going to send each receiver to 2 to the 255. What's 2 times 2 to the 255? 2 to the 256. That's 1 with 256 bits of 0. You get rid of that leading 1. It's 0. So I am transferring 0 right here. So the count is 2, so it passes that. The value is greater than 0. Balances messages.sender, that is greater than 0. Because amount is 0, this subtracts nothing from my balance. So yeah, the two checks pass. 261 does nothing to the balance. And then in 263, this is going to transfer to each one of those receivers 2 to the 255th, basically 2 to the 255th in value. So there's where an overflow costs you a bunch of money, and that's basically what happened in the exploit 2 slides ago. Okay. So remediation, validate all arithmetic operations is the solution to this. So if you have something that looks like this is the unsafe add pattern. Seller balance is equal to seller balance plus the value. You have to make sure that that thing doesn't overflow. Every single arithmetic operation can't overflow. So you have this safe add, and the safe add with that amount of value, you would require that when you add the value to the seller balance, it better be greater than the original seller balance. If it's not, you have some kind of overflow going on. So then you only do that operation if that holds. Okay, so this is why we use safe math everywhere in a Solidity contract. If you see a Solidity contract doing math without using safe math, it's probably got a vulnerability somewhere in it. And the way we do it is through defining a library in Solidity. So this is the safe math library. I take a multiply, and I do the multiplication. C is equal to A times B. And then I check to make sure that A is equal to 0 or C div A is equal to B. So you get the result back. And then you can return C. All right. And so this is what you would want to do whenever you're doing addition in Solidity, is to use the safe math implementation, and then instead of doing addition, you would do something like A.add.B. Okay, so for this vulnerability, you have a level in the CTF, which I'm going to do a walkthrough for you. This is token sale. So here's if you deploy the level, you get to the level website, and you get something that looks like this. Security Innovation is doing an ICO. They're releasing 1,000 SI tokens, and each SI token is 1 ETH. And you are allowed to purchase via their Web3 web app. So this, if you click on, let's say, purchase SIT, it'll bring up MetaMask. It'll say, yeah, send this contract 1 Ether, and then you'll get a token. You'll have bought the token in that smart contract. This particular smart contract allows you to get your money back. It's got this refund function that says, you know what, if you're unhappy, you can return your tokens, but only get 50% of your tokens back, of your ETH back. So any money that you put into there, if you try and refund it, you'll only get half of it back. And your goal is to get all of it back and then some. You're trying to wipe this contract completely out. The actual implementation of the token takes from OpenZeppelin, the standard ERC20 token implementation. So again, this is vetted code where you're pulling from ERC20, and as part of ERC20, it implements this standard token contract. And you're going to create your own token that is a derived class from the standard token. And this is what you would typically do when you do an ICO. And this is the implementation. This is a constructor for SI token. It's giving itself a name. It's giving itself a symbol. It's creating an initial supply of tokens that it wants to implement. So in this case, there's 1,000 SI tokens. And it's done in ETH. The units are in Ether. And then it is going to implement some commission. So there's a fee amount for every transaction. So anytime I buy tokens, it's going to take a cut off the top. And then it's going to keep track of the amount of ether the contract has collected, and then specify an address for the developer so that the developer can withdraw all the ether after the sale. Okay, so that's what these pieces are. So when you deploy the contract, or if you reset the challenge, so if you've solved it already, you'll get this reset thing. If you haven't solved it, when you click the button to deploy it, what happens is the CTF is going to create, the CTF launcher is going to create a new level and call the constructor. And the CTF, it gets initialized with the launcher address and the player address so that, only you two can access this contract as before. It sets this fee amount to 10 Zabo, and it sets the developer to the message.sender. And so the message.sender in this case is the CTF launcher. So it's just every level has a launcher address. And so this is this message sender is the launcher's address, which you'll be able to pick out the address from Etherscan on this. So it's the CTF launcher is the developer. And what this does, it will take this constructor is payable. So you see up here it's payable. And when the game launches this level, it will launch it with the 0.3 ether that you have provided on deployment. So when you click on that, it's going to ask you to fund the contract deployment with 0.3 ether. That gets put right into this constructor, and the constructor will then call this purchase tokens with your 0.3 ether as the value. That's the amount of money. Okay, there's also a fallback function that allows you to purchase tokens. So if I, from my wallet, after the thing is launched, I want to buy some tokens, I can send money directly to this contract address, and it will call the fallback function to purchase tokens. And the purchase tokens function is here, and it mimics an ICO. You'll note that this call is internal, so that it can only be called via the fallback function. It requires that you have to be able to, you're purchasing some tokens, and that you still have in the ICO, so balances this, keeps track of the amount of tokens the contract has available. It starts out with 1,000. You cannot buy tokens if the contract doesn't have any to sell, and so that's what this require is doing. If both of these hold, then what happens is for whoever is buying the tokens, you update their balance, their token balance, to be the amount that they sent minus the fee, because you're charging a 10 Zabo fee, and then you update the balance of the contract's supply of tokens, and then you give the fee to the developer. So that's what this is. You supply the developer that fee, and then you update the amount of ether that you have in this ether collection variable, and you get because you've gotten message.value worth of money, that's what you updated at. You could have also done plus equal to underscore value in this case. Okay, and then here's the refund tokens. It allows you, if you are trying to get a refund, you specify the amount you want refunded. It calls this transfer function, which is part of the standard token implementation, to make sure that you have enough. So that's what this is. It calls into the standard token base class, and the standard token base class makes sure that you have enough tokens in your balance before it'll do the exchange. And it's doing the exchange using safe math because it's smart, smarter. So that's what that function is doing. And then if so, it does the transfer first, and then it updates the ether collection to say, you know what, I'm going to transfer half of the value of what they wanted refunded back to the sender, and then I'm also going to update my ether collection variable. Okay, so it keeps half of the ether. So where was the vulnerability? Yes. Value needs to be less than the fee. So if you look at this, It's not checked. This statement right there is never checked to make sure that the value is greater than the fee amount. Okay? But we have a web page, and this web page is awesome. Look at how well it's written. The value must be greater than or equal to 0.001 before I allow you to purchase a token. And look, it's got this pop-up. So this pop-up makes sure that you can't do that. And y'all are laughing. Why? What's so funny? Doesn't this work?
We've taken a class from you.
That's not true. Yes. So you should be, yeah, I don't want to diss front-end developers, but like just fixing it on the front end doesn't fix it on the back end. And you've seen this everywhere where you do the input validation on some JavaScript on the front end, and then you decide, well, that's good enough. Who would ever try and go directly to the back end to do this stuff? People will go directly to your back end to do stuff. And that's what the issue is. But, so you must add protection within the contract itself, but can we call purchase tokens directly? Like, look at all this security. I used internal to limit the access to purchase tokens. So you cannot call purchase tokens directly. Does that secure it? You could subclass it. Well, in this case, it's not subclass, though. So in the contract you're trying to exploit the contract as it's written. But if you look, so purchase tokens, you can't call purchase tokens directly with your value that's less than fee amount. So you can't just say, so I can't call purchase tokens with like, half a Zabo to do this. But if you look, how is purchase tokens called in this contract? It's done through this payable fallback function that is external. So then all I need to do is send this contract some tiny amount, something less than the fee amount, and then something less than 10 Zabo, and then you can pull off the underflow. Questions? Because that's what you'll be doing, hopefully soon, if I can hustle through here. So you send the contract a value smaller than the fee amount to cause a downward overflow, downward underflow, an underflow. I'll fix that. And then the underflow allows you to own more tokens than you purchased by a lot. And then you can call refund token with 2 times the remaining balance of the contract to zero it out. Because you're doing a 2-for-1 swap, you have to calculate exactly how much that would be to wipe out the contract, which I'll go through in this walkthrough. So the first thing you do, you bring up MetaMask, you copy the contract that you're trying to attack, the address of the contract you're trying to attack. You say, I want to send that contract some tiny amount. So in this case, say I want to send it 9 Zabo, and the fee amount is 10 Zabo, so then I'll end up with 2 to the 255 minus 1 Zabo in my balance. So I'll copy the contract address. I will send that contract address. In this case, the amount that I'm going to send is 9 Zabo, and then this will cause the underflow and purchase tokens. I'll now have a balance that's enormous. I can use the balance of call from the standard token base class to show that I've done this underflow. So that's what you can do. You can call balance of, and if you call balance of on the contract, on the base contract, and you give it your owner address, you can see the underflow has happened. That's how many tokens I have in this contract, which is way more than I need to wipe it out. If you get 0, and make sure you're reading from Ropsten. So that, I put that in there because people, like when you go to, this is from MyCrypto. When you go to MyCrypto and you try and get the balance of that contract and you get 0, it's because you're on the wrong blockchain, probably. Okay, and then what you can do is you read the amount of ether in that contract. So ether collection was that variable that keeps track of the amount of ETH in there. So what you do is you figure out how much there is, and then you multiply it by 2. Because when you refund your tokens, you're going to get half of that. So if you really want to wipe out everything, then you take 2 times the balance, call refund tokens with that, and then you wipe out the contract itself. So there's step-by-step instructions in the labs, but that's effectively your homework for this vulnerability. So it's pretty straightforward. And then you call refund tokens with that value, and then you win the level. Questions about what you're going to do for this particular vulnerability? Okay. And then you'll get the winner thing. Okay, so the call will sometimes fail. This is the blockchain. Stuff fails all the time. If it fails, you can either try again later or make sure, let me see. Or you can increase the fee amount as well. So hopefully it just works. I'm crossing my fingers, but I'm going to put that out there just because I know stuff doesn't work sometimes. Okay. All right.